In our last deep dive, we explored how text is broken into tokens. But tokens are just markers. To truly understand meaning, models use embeddings, the geometry of language. An embedding is a numerical representation of a token in the form of a vector, a long list of coordinates that defines its position in a multi-dimensional space. While we visualize this in 3 dimensions, modern models like BERT or GPT use hundreds or thousands of dimensions to capture the vast complexity of human thought. The power of this space lies in proximity. Words with similar meanings or contexts are placed closer together, allowing the model to calculate semantic relationships. Models often use cosine similarity to measure this relationship, calculating the angle between vectors rather than just their distance to determine how related two concepts are. Early models used static embeddings like word2vec, where each word had a single fixed position regardless of its context. But language is rarely that simple. Consider the word bank. Is it a financial institution or the side of a river? Static embeddings struggle with these homonyms, often averaging their meanings into a single point. Modern transformers use contextual embeddings. The position of a token in vector space shifts dynamically based on the words surrounding it, capturing its exact meaning in that moment. This happens in the embedding layer, the very first part of the model's architecture. It's a lookup table that transforms discrete IDs into continuous numerical signals. Each dimension in a vector can be thought of as a latent feature, though they are often abstract and difficult for humans to interpret directly. These embeddings aren't hard-coded. They are learned during the training process as the model adjusts their positions to better predict the next token in a sequence. Because they capture so much knowledge, pre-trained embeddings can be transferred to other tasks, giving smaller models a head start in understanding language. In multimodal models, even images and audio can be mapped into the same vector space, allowing an AI to see the connection between a picture and its description. This has led to the rise of vector databases, which allow us to store and search through millions of embeddings for applications like RAG and semantic search. To visualize these massive spaces, researchers use dimensionality reduction techniques like TSNE or UMAP to project high-dimensional data into 2D or 3D maps. However, embeddings can also inherit biases from their training data, potentially encoding harmful stereotypes into the very geometry of the model's understanding. Identifying and mitigating these biases is a core challenge in ethical AI development, ensuring our model's geometric representations remain fair and accurate. At their core, embeddings prove that meaning can be treated as a mathematical property capable of being transformed and optimized. In summary, tokens become vectors, which are placed in high-dimensional spaces to represent semantic similarity and context. Understanding these geometric foundations is essential for anyone looking to build, optimize, or fine-tune local LLMs effectively. The next time you see an AI generate a perfect response, think of the vast, high-dimensional space it just navigated to find those words. If you enjoyed this deep dive, stay tuned for our final episode on the transformer architecture. Don't forget to hit that follow button.